let's talk about consistent hashing, one of the most amazing and popular algorithms out there. Remember, there are huge number of misconceptions out there with respect to consistent hashing. We'll debunk all of them. But always remember, consistent hashing is not a magical solution. Consistent hashing is not a service. Consistent hashing is an algorithm that helps you answer just one question: who owns this data? That's it. The only thing that it solves for is data ownership and nothing else. Nothing else. Right? So, in this one, this will be a very detailed video. So, we'll understand the need of consistent hashing, hash based routing, consistent hashing. We'll go into scaling up, scaling down, and in exercise, I'll give you a place through which you can implement your own consistent hashing. It's really easy to implement. Please do it. Please implement consistent hashing rather than just looking at it from a theoretical perspective. Right? Okay. Stay with me. You'll understand consistent hashing to the fullest. Okay. First one. Let's understand what ownership is. Ownership, you need it in order to understand who owns this part, not just data. For example, who will handle this request? Who owns this data? Who will handle this? Who manages this partition? Something like that. When you want to understand the ownership, there are multiple ways to do it. One of the most common ways is hash based ownership. Right? For example, say we have a load balancer. Right? When a user connects to a load balancer picks a server and it forwards the request to that server. That server does its thing, sends the response to the load balancer forwards the request to the user. This is how typical load balancer works, right? But now, how does load balancer figure out which server to forward the request to? One of the popular ways to do that is hash based routing. So what you do is, depending on the request, you take hash of something. Let's say hash of IP address, hash of request ID, hash of user ID, anything. Let's say hash of user ID. You take hash of that user ID, you do a mod 3 because you have 3 backend servers. It gives you one of them, let's say 0. So you forward the request to 0. Now the hash function could be anything, SHA-256, SHA-128, anything that you would like. But the idea is, you take a request for a particular user, you extract that user information from the request, pass it to the hash function, you get a value which is 128 bits. For example, if you use SHA-128, you mod it by 3, you get either 0, 1 or 2. Depending on what you get, you forward the request to that corresponding server. Right? Now if you look carefully, this logic is very simple. Do you need a service for that? No. It's just a hash function. So when a request comes in the load balancer, when the request comes in, it extracts the user information out of it, pass it to the hash function, gets the value, does the mod, forwards the request. It's not a service. It's a function, a simple function, not a service, right? So your hashing logic is a logic. It's just a function that you're invoking, correct? Where does it reside? It resides in the load balancer, in the request handler of the load balancer, that hey, which backend server should I pick to? It does not make another call to a service, right? We just don't add random microservices just for the sake of it. This is how real systems are built, right? So when the request comes in, load balancers knows this is a request come in for this particular user, passes it through the hash function, mod 3, gets the server, forwards the request, gets the response, sends back to the user, correct? Okay. Now let's see what happens when a particular server is taken down. Let's say you were over provisioned. You handled peak with 3 servers, good enough. Now you see very mediocre traffic. So you want to trim down a particular server. You want to remove a particular backend server. So now what would happen? So now the request, when you remove a particular server, what would happen? Your hash function would change. Your load balancer would know, hey, earlier I had 3 servers, I was doing mod 3. Now I have 2 servers, I have to do mod 2. So everything else remains the same. It just changes mod 3 to mod 2. So when the next request comes in for any user, the request comes to load balancer. Load balancer says, hey, this is the request, this is the user ID. I'll pass it to the hash function, let's say SHA-128. Then I do mod 2. I get either 0 or 1. So if I get 0, I send it to backend server 0. If I get 1, I send it to backend server 2. It sends there. So if you look carefully, if you just remove this one server, there was no hiccup at all. The next set of requests that came in went to the corresponding server. No problem, right? But why is that not a problem anymore? Because load balancers are stateless. That backend servers are stateless. Because no matter where the request goes, it would be handled. Because it is not maintaining any state for them. Depending on the request, it sends to one of the servers. Every server is equally capable. This is the most important thing. Both or all the three backend servers were equally capable of handling any incoming request. This is statelessness. If everyone is equally capable, which means it does not matter which server your request is forwarded to handle that request. So, which is why even if you remove backend server 1, it's okay, your request would be balanced between the two. No problem. Right? This is why we see hash-based routing as one of the most common ways of routing for stateless backends. Typically, load balancer plus API server that we see, in most cases, your load balancer is configured with hash-based routing. Round robin is also there, but hash-based is more common than that. Got it? Okay. But now, what happens when, let's say, instead of API servers, which are stateless, let's say you have something stateful. Let's say distributed storage. Fancy words, I'll help you understand. So let's say you have a proxy, load balancer kind of stuff, but proxy is a better word for this. So now let's say you are having a distributed storage. So instead of API servers, you have storage nodes, right? You have a distributed key value store. Given a key, store it there. Given a value or rather given a key, store the value. Given a key, get me the value, right? But now here, the storage is distributed. It means that there is no one database where it is going to. The proxy is using hash-based routing to route the request to a corresponding server. Now, how does proxy is picking it? Proxy is using hash function to do it. So given a key, let's say your user says, hey, please store this key for me. This key value. It takes the key, pass to the hash function, gets some 2 raised to power 120, like for 128-bit number, mod 3, it gets 0, 1, 2. Let's say it got 1, so it stored that value over here. Right? So it knows that this node owns the key. This is what I'm talking about, ownership. Who owns it? Right? Okay. So request came in from the user to the proxy, picked the server to store that key, and done. So next time when a request comes in for the same key, it would go to that same server because hash function remains the same. The output of the hash function for the same key remains the same, which means that no matter how many times I get request for the same key, it will always go to the same server. So all the requests for key K3 and K5 will always go to node 1. For key K1 and K4, it will always go to node 2. For key K2 and K6, it will always go to node 0. Statefulness maintained. Because now with this hash function here, we are ensuring that all the requests of a particular key always goes to a particular node. Stateful. Right? Which is what we wanted, because this node is holding the data for K3 and K5. What if this just at random sends request to node 0 for K3? It does not have the data. Now what would happen? Miss, right? That's the problem, which is why we are determining ownership through this. That you take the key, pass to the hash function. This would always remain the same for the same key. Mod 3, you'll always get the same node where you would want to store the data. Right? Now let's say we stored these 6 keys and the way it is distributed as K1 goes to node 2, K2 goes to node 0, K3 over here, K4 to node 2, K5 over here, K6 over here. Right? So let's say this is the distribution. We'll use this example to build a deeper understanding of consistent hashing. Right? Okay. Now, similar to how we removed the backend server in case of load balancer and it did not affect at all, what if we remove over here? Now, if we look closely, because a key is owned by a particular node, let's say if I just remove this node, I cannot just pass the request of K3 over here because K3 does not exist in node 0 at all. Right? This is where the problem is. If I remove this or if I add a new node in the system and this hash function changes, it's not going to automatically work because output of hash function remains constant. But when you change hash function mod 4, suddenly the routing, or sorry, suddenly the ownership has changed dramatically. Let me take an example to help you understand about repartitioning. So now what happened? Let's say when you change the number of nodes and you removed a particular node. Let's say you removed node 2. So now what happened is your hash function that was part of that proxy is now f of n, it's a function of k mod 2. So now what needs to be done? When you remove a particular node, now you have to literally go through all the keys that you have, pass it through the hash function and see now which node owns it. And then you move the keys around the nodes. For example, we had mapping that looks something like this. First key k1 went to node 0, right? But now I will go through key k1 because now my hash function has changed. I will pass key k1 mod 2 and let's say I get 0, which means k1 that was part of node 2 now goes to node 0. So I have to literally copy key k1 before my node 2 goes down. I have to copy key k1 and move it to node 0, right? Similarly, for key k2, it went to 0, but now my hash function changes to mod 2, now it spits out 1. So I have to take key k2 which belonged to node 0 and move it to node 1. Similarly, for k3, but look carefully, for k3 it was at 1, but with new mod 2 function, it's still at 1. So k3 does not need to be moved. Similarly, k5 and k6 does not need to be moved. 1 0 1 0. But let's say key k4 which went to node 0 now needs to move to node, which went to node 2 now needs to move to node 0. So if you look carefully, we are doing almost 50% of data transfer. 3 keys moved out of 6. This is a problem. This is a huge amount of data point. Now imagine there are millions and billions of keys out there. This is a huge amount of data transfer that you are doing. This is a limitation of hash-based routing because you are giving your power to a hash function. And now as soon as your hash function changes, suddenly your mapping changes. So before you take down your node or you scale down your data node, you have to ensure that entire thing is rehashed and understood the new ownership, that who owns what, before you start serving the new thing. So can we minimize data movement? This is where consistent hashing comes in. We spent last 12 minutes understanding why we need consistent hashing. I hope now that is clear. Now we'll go into the next part, that what is consistent hashing. So as I always say, just like how hash-based routing helped you determine ownership, that who owns what, which node owns which key, or the which key is owned by which node. Consistent hashing also answers the problem of ownership, who owns what. And what consistent hashing is not, consistent hashing will not do data transfer for you. Consistent hashing is not a service that magically works. Consistent hashing is just like this algorithm, not even algorithm, that's an exaggeration. It's just a simple function call that just tells you who owns it. That's it. You have to take care of data movement. You have to do whatever with it. It would just, you give a key, you pass it this the configuration, it would tell you which node it belongs to. That's it. That's all it does. Right? That's the job of consistent hashing. Nothing more, nothing less. Right? Now let's see, a very popular way to look at consistent hashing is as a ring. Right? But implementation, we'll talk about in 2 minutes. So now let's see what this is all about. Consistent hashing. So a hash function. So first thing, just like we had hash function, the fn that we see over here, that same thing. Let's say we use SHA-128 hash function. So SHA-128 implies it takes any key, passes through the hash function, and it generates a 128-bit representation. 128-bit implies the maximum value. So the range is 0 to 2 raised to power 128 minus 1, right? So that huge of a range is what we are talking about. But obviously we will not take that huge as an example. We take a smaller range as an example. Let's say 0 to 15, 0 to 2 raised to power 4, right? This is what we are taking, small example to understand it, right? Okay. So we have the hash function, the exact same hash function that we saw before. That same hash function comes over here, but without mod, right? That's the difference. Now what happens is, every storage node occupies a slot in the ring. Now, what does it mean when it say occupy? That we'll talk about. So for example, I am a storage node, let's say node 0. When I passed my IP address of node 0 or something like that, some identifier through the hash function, I got value 3. When I got value 3, which means my node 0 is placed over here. Let's say I pass node 2 through the hash function, I got value 8. So my node 2 stays over here. And my node 1 got slotted at 12 over here. Remember, our range is just 0 to 15, but in reality it is 0 to 2 raised to power 128. Here it is only 15 is what we are playing with, so that we understand it. Right? Okay. So now this is a ring. Now this ring, in actuality, it looks like a ring. Does not mean you have to implement a linked list. No. In reality, it is modeled as a simple array. Literally array with 3 elements. 1, 2, 3. Placed in order. First element this, second element this, third element this. Why? Because slot 3, slot 8, slot 12. Literally one after another in an array of size 3. That's it. You don't have to implement ring sort of stuff. It's very simple implementation. I'll share links through which you need to go through to understand the implementation. Right? Okay. So what next? The ring will help us, will tell us who owns what, but how? Now, what happens? Oh, before that, the array that we were talking about, this is an array of 3 elements. Node 0, node this, literally array. Where it's a stored part of proxy. It's again a function call, just like how hash function we made a function call SHA-256 mod 3. Same thing over here. It's just a function call, not a service. Consistent hashing is not a service. It's a simple function call. Right? Okay. So now what happens is you have this 3 node physically looking something like this, but in a ring placed something like this. Right? You have defined some order to this. Now what we do? We want to know, let's say I have key K1. Who owns key K1? How would we know that? So what we do is we pass key K1 through the exact same hash function, SHA-128. We get output as, let's say, 0. We get output as 0, so key K1 is slotted over here. But who owns key K1? The node which is immediate right of it, immediate clockwise of it, which is node 0. So this node owns key K1. Now let's say I have to determine ownership of key K2. Who owns key K2? Let's say when I pass key K2 through the hash function, let's say I get value 10. The node to the right of it is where my key is stored, which is node 1 at slot 12. Right? So this very beautifully answers the question, who owns a particular key? For you to determine the ownership, you take the key, pass to the hash function, find a node to the right of it that owns the key. Simple. Right? Now this is what consistent hashing is doing. It is just telling you who owns this particular thing. Consistent hashing. That's it. That's it. Nothing more, nothing less. Now let's see what happens when we scale up, because we need to solve a problem. The problem is data movement. So now let's understand how this data movement problem is solved. So now let's say my 3 node cluster is not good enough and I want to add one more node to it. So let's say I had node 0, I had node 1, I had node 2. Now let's say I've added node 3 to it. The first thing that I'll do is I will go and pass the IP address of the node through the hash function. Let's say it spit out 1. So where is my node placed? At slot 1 over here. So now if you look carefully, the key K1 that got slotted at 0, which was owned by node 0, will now be owned by node 3. Correct? So the keys that got affected when I added node 3 in the slot 1 were all the keys that lie over here. Because all the keys that lie over here, they used to go to node 0, but are now will now go to node 3 here. Got it? But if you look carefully, all these other keys they used to go to node 2 will now continue to go to node 2. All these keys that used to go to node 1 will now go to node 1. No changes there. So if you look carefully, the only keys that got affected is this small fraction, while every other key remains as is. Minimal data movement. This is what we are talking about. That you don't have to rehash all the keys. You are just rehashing some of them. And you exactly know which ones are affected. These ones are affected. So any keys that hashed in this slot are affected. But practically, how would you do it? Because would you still have to go through all the keys? No. Because the keys, these keys, they were anyway going to node 0 are now going to node 1, which means these keys will be present in node 0. So you literally have to just take a snapshot of node 0, literally a snapshot of node 0. You create a node 3 using that snapshot and you delete the keys that are not hashed on that part, right? So that are not hashed on this node anymore. Just iterate through it and delete the unhashed, the unused keys over there. Simple. It's that simple operationally, and that's the beauty of this algorithm. That it is not only simple to understand but also simple to implement. It is very operationally efficient. So for you, again I'm repeating, for you to do this operationally, it's literally that you first take the snapshot of this node. Now first of all, you know that your node is slotted over here. So you go to the right of it, the first node that you find on the right, because keys that were going to here will now come over here. You take the snapshot of it, create this new data node using the snapshot of it. Then you add this snapshot or you add this node to the ring, start serving the request and delete the extra keys from this node that you just moved over there. Simple. Simple. It is so operationally efficient to do it. No, you are not even touching the keys in other nodes. Not at all. Just the node to the extreme, just the node to the immediate right of it is getting affected. That too, a snapshot of it which is very fast, spinning up, adding it very fast and whatnot. It's very simplistic. This is the beauty of consistent hashing. Now, similar to how we did with scale up, we can do something very similar with scale down. So let's say I'm now deleting node 0. I don't want node 0. Which keys are affected? The keys that used to go to node 0, these keys, they used to go to node 0 will now start to go to node 2. So the node that is to the immediate right of the node that I'm deleting, that needs to handle a little more traffic. Obviously you are scaling down because you are over provisioned. So what you will do, you will literally take all the keys from this and copy it over here. Simple, dump and load over here. And you remove this node from that. Problem solved. Operationally, it's so simple. Other node is these keys that are hashed over, these keys that are hashed over here are, and these keys that are hashed over here are not even getting affected. The only keys that get affected are these one. But you don't really have to know the keys because you are anyway copy pasting everything that you have on this node over here. It's not that some keys will go on this node, some keys will go to this node. Not like that. You literally copy paste everything from here to here. Operationally, it is so simple. This is why consistent hashing is so popular. And again, I would reiterate, all it does, it answers the problem of data ownership. It will not do data transfer for you. It will not do anything. It will not do anything operational for you. But this is what this function would do. Now, let's talk about implementation. First of all, whatever I discussed, go through the video one more time and understand consistent hashing in depth. First. Second, read the blog. I posted it in 2020. I wrote the implementation of consistent hashing using array, simple array and binary search. That is it. It's really simple implementation, not at all complex. So implement it in your favorite programming language, which is where you will understand when I say it's just a function call and not a service, right? So first, understand consistent hashing. If it requires, go through the video one more time. You need to have a solid understanding of it, number one. Second, read the blog. It's there on my website, arpitbhayani.me/blog/consistent hashing. It has a Python implementation of consistent hashing. Do that. Implement, not Python, pick your favorite language and implement it. It just takes one array, or rather 2 arrays to implement it, and it's really simple. You just keep the array sorted, that's it. And 2 is also an overkill. I could do it in 1. 2 is an overkill, but it's very simple. Just requires one binary search for efficiency and one array. That's it. Really simple implementation, but do it. This way you'd understand how consistent hashing is implemented. Not just theoretical jargon of how drawing the rings and whatnot. Drawing rings is visually appealing, makes things easy to understand, but the real fun is you would have to implement it someday. So go through this blog. I wrote it in 2020. Please implement it. You'll learn, you'll have quite a bit of fun while implementing it. Trust me, and I'm not even exaggerating when I say you'd love the implementation of it, right? And again, I would highly recommend you to build a detailed understanding of it and think about every single system, every single thing you learn from the practical perspective. Think of implementation at every single stage. System design is not theoretical. System design is completely practical. You just need to find ways to implement it. Consistent hashing is not theoretical jargon. It's really practical. Implement it. Here is the blog for you. Go ahead and implement it. Take your time. There is no hurry at all. Take your time, implement the things, and you form a detailed understanding of the subject. And yeah, this is all what I wanted to cover as part of consistent hashing, right? We spoke about operational aspects of it. We spoke about details of it. We spoke about need of it. Understand it to the fullest. And yeah, this is all what I wanted to cover. I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks a ton.